Hello and welcome to the last of the lectures in this week 11 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will discuss the monotonicity of a similarity-based reasoning scheme. Let's begin by recalling some of the basic components of fuzzy sets that will come into play in this lecture too. We know, given a fuzzy set, we could talk about its support, height, the kernel or the ceiling of this fuzzy set. Given a fuzzy set, we know what an alpha cut is. It is essentially all those elements of X, the underlying domain, whose membership value is greater than or equal to alpha. A fuzzy set is said to be convex if every alpha cut of the fuzzy set is convex. Note that alpha cuts are actually subsets of the underlying domain. So we want the underlying domain to be a space in which convexity is defined. Essentially, we take it as a vector space. We say a fuzzy set is bounded if its support is bounded, otherwise it is unbounded. Now, we have seen two different types of orderings between fuzzy sets. One is the pointwise ordering. We say that A1 is ordered with respect to pointwise ordering. A1 is contained in A2 if and only if its membership values are smaller than the other one. So A1 is contained in A2 if A1 of X is less than or equal to A2 of X for every X in X. So clearly, if you look at these two pictures, we see that in one case A1 is contained in A2, in the other case A2 is contained in A1. And we have seen that often these kind of fuzzy sets are not orderable with respect to this pointwise ordering. This led us to discuss level set based ordering, wherein what we took was for each alpha cut, we looked at the corresponding alpha cuts and we ordered them based on the intervals there. We have seen this, that the pair of sets on the left hand side to your screen, they are orderable with respect to this level set based ordering, while the ones on the right, they are not. Well, we know what are fuzzy coverings and partitions. We will introduce one more in this lecture. So by a fuzzy covering, we mean a collection of fuzzy sets over X such that the union of support of these pieces that we picked up in the set, they actually contain the set X itself. So the union of supports of these fuzzy sets contains X. Another way to look at it is that for every X in X, there exists some AK in this collection to whom X belongs to some non-zero membership degree. This is just a simple basic fuzzy covering. We also defined what is a fuzzy partition. One particular type of partition is called the Ruspini partition. Here what we expect is that for any X, the sum of its membership values to every piece in the partition, the collection, it adds up to 1. So we have seen this figure. In this lecture, we will introduce what is called a Sub-Ruspini partition. What is this? In the Ruspini case, we wanted that sigma over k, ak of X is equal to 1 for every X. Here, we allow it to be less than or equal to 1. That means the sum of the membership degrees to the pieces in the partition need not add up to 1. However, if it does add up to 1, then it can add up to 1 only if that X is a point of normality for some element in the partition. Now, how does it look like? So look at this. This is exactly the set, collection of sets which we saw as a fuzzy covering because the union of its supports contains X. However, it is also a sub-Ruspini partition. Clearly, it is not a Ruspini partition because if you take a value here, then it belongs only to A2 and not to degree 1, which means so it does not satisfy the Ruspini condition. However, it is a sub-Ruspini partition. Why do we say this? If you add up for any X, if you add up the corresponding membership values of the sets to which it belongs, of the fuzzy sets to which it belongs in the partition, we see clearly it is less than or equal to 1. And not only that, only at points of normality, there are no intersection, which means the sum actually is equal to 1 only at those points. other points the sum of membership degrees is not equal to 1. Clearly in this case, among the 5 sets that we see, A1, A2, A3, A4, A5, at any point of time only 2 of them are intersecting on the space. So for any point x, it at most belongs to 2 fuzzy sets, and clearly you see that the sum of those membership degrees is not equal to 1. Where it is equal to 1 is only at these points of normality. So it is clearly a Sub-Ruspini partition. We will see that these kind of partitions are useful when we want to discuss the monotonicity of an SBR scheme. Well, we have seen another type of classification of rule bases. We say that given a single input, single output rule base, n of them, we say it is monotone if you pick any 2 rules, AI implies BI and AJ implies BJ, we say it is monotone if whenever AI is ordered, AI is less than AJ, then it should also hold that BI is less than BJ, where this is the level set based ordering on fuzzy sets. Now, if you consider these 3 fuzzy sets, A1, A2, A3 and B1, B2, B3, they are clearly orderable with respect to the level set based ordering, alpha cut based ordering. And so if you take them as fuzzy sets on X and these are fuzzy sets on Y, then we could consider them as antecedents and them as the corresponding consequence. And if you make such 3 rules, then it will be a monotone rule base. Because clearly A1 is less than A2 is less than A3. Similarly, B1 is less than B2 less than B3. This is again with respect to the alpha cut based order. Now, we want to discuss the similarity based reasoning. A quick recap of the mechanism. What do we have? Once again, we have a CISO rule base. We are given an A dash, which is a fuzzy set on X. What we do is we use a matching function to match this A dash to each of the antecedents EI and obtain similarity values SI, S1, S2, so on to Sn. And these are the 2 important or commonly used matching functions in the literature. The next step is we take each of these similarity values Si and modify the corresponding consequent Bi. And towards this, we use a modification function J. And we have seen that even though J is from 0, 1 cross f of y to f of y, because Bi's are fuzzy sets on Y, these are modified into fuzzy sets again on Y. So J is a function from 0, 1 cross f of y to f of y. Essentially, since we are dealing only on the membership functions, working with the membership values, it is clear that J can also be considered as simply a binary operation on 0, 1 to 0, 1. These are some often used modification functions. In the third step, we take all these modified consequence, B1 dash, B2 dash, so on till Bn dash, and we aggregate them. Once again, it's like collection of fuzzy sets on Y. We aggregate them to obtain a fuzzy set on Y. However, we have seen essentially we are only playing or operating on the membership values. So G can also be thought of as simply a binary function on 0, 1 to 0, 1. And if it is associative, it can easily be extended to an n-ary function. We have seen that often there is a need to defuzzify it, not leave it as an obtained output fuzzy set, but defuzzify it. That means obtain a value y on the underlying domain y. Similarly, often we are given only the x from the domain input domain x. We need to suitably fuzzify it to an a dash so that it can be fed into a fuzzy inference system. So these are 2 operations, a defuzzification operation and a fuzzification operation. So totally there are these 5 steps. Well, in terms of the form, we know that there are these many parameters or degrees of freedom that we have. Px and Py are the coverings on, fuzzy coverings on X and Y. They give rise to the rule base where the A's come from Px and Bi's come from Py. They form the fuzzy if then rule base. M is any matching function, J is any modification function, G is an aggregation function, H is the fuzzifier, and G denotes the defuzzifier. Let us now discuss the monotonicity of an SBR inference scheme. We have seen that a fuzzy inference system can be discussed at 2 levels, one at the classical level as a function from x to y. If you consider f star to be the system function of an FAS, given an x dash from x, we could apply a fuzzifier, a fuzzification process, obtain an a dash and map it using the psi tilde, which is essentially a function from f of x to f of y. So we obtain a b dash and then defuzzify it using a defuzzifier g down to the output domain y. So f star could be looked at as a mapping from x to y. Of course, psi tilde is a mapping from f of x to f of y. Once again, we will discuss monotonicity of SBR inference scheme also only at the level of classical sets. That means looking at f star as a mapping from x to y. Now, we have seen in the case of discussing SBR inference schemes with respect to their interpolativity or continuity or robustness, that it almost always entails that some conditions or restrictions should be put on the matching function. In that context, we have introduced a few consistency properties on matching function M. We will introduce a few more in our quest towards discussing monotonicity of an SBR. Given an M, which is a function from f of x cross f of x to 0, 1, we say it is consistent with the set of fuzzy set that we are considering if it simply ensures that for identical inputs, if a pair of identical inputs is given, then the similarity value should be 1. That means m of a should be equal to 1. Given a fuzzy covering p of x, px, which is essentially a collection of fuzzy sets on x, which covers the domain x, that means the union of supports of these fuzzy sets contains x, we say M is consistent with respect to this px if for any a dash that we get from f of x, this inequality is held. What does it say? When we compare a dash with ak for each of the pieces in the partition, the fuzzy covering that we considered, the sum of the matching values, the similarity values, should not exceed that of 1. This another condition that we could insist on M, which is called the insistence condition on M. M is said to be insistent on f of x if for any a dash coming from f of x, the similarity value between a dash is greater than 0 only if the supports of a and a dash actually intersect. Whenever they intersect, it should be greater than 0, and if it is the similarity value of a and a dash is greater than 0 as calculated by the matching function M, then it should imply that their supports, corresponding supports, are in fact intersecting. Given f of x, we could consider many orders on it. So we say a matching function M is specific with respect to the ordering that we consider on f of x. To begin with, we consider a poset. We know that on f of x, for suitable subclasses of f of x also, we can consider many orderings which will make it a partially ordered set. We say M is set specific on f of x with respect to the order that we consider if for any three fuzzy sets a1, a2, a that we take, whenever a1 is smaller than a2 with respect to the ordering that we consider, then m of a1a should be greater than or equal to m of a2a. So here we are ensuring that the more specific a set is, the more similar it will be to a given fuzzy set A. So somehow it retains or preserves specificity. As an example, if you consider the Smith-Magre matching function, it can be seen that in fact it satisfies this MSF with respect to the pointwise ordering or any f of x that you can consider. Now let's come to discussing the monotonicity of an SBR as a mapping between classical sets. So that means we are looking at f star and discussing f star, the monotonicity of it with respect to the alpha cut based ordering. So once again, we start with a strictly monotone rule base. That means we have the antecedents ordered in a particular way with respect to the alpha cut based ordering, and also the corresponding consequence are ordered in the same fashion. we consider a special class of fuzzy sets which we denote as f star of x, and A belongs here means A is normal, convex, continuous, and it's strictly monotone on both sides of the ceiling, and since it is normal, that means it's strictly monotone on both sides of the kernel. Well, we also want to introduce a special class of fuzzifiers. We know a fuzzifier H is a mapping from x to f of x. We want that this fuzzifier satisfies the following two properties. Whenever x dash is smaller than x double dash, then the fuzzified output that we get from x dash, which let's call it a dash, this should be orderable with respect to the alpha cut based ordering with a double dash, which is the fuzzified output that we get for x double dash. So a dash and a double dash are the fuzzified versions of x dash and x double dash. If x dash is smaller than x double dash, then we want that the corresponding fuzzified versions a dash and a double dash should be orderable with respect to the level set based ordering. Of course, within the same ordering fashion. We should preserve the monotonicity of the ordering. And if this Px is a covering that is given to us, let it consist of n such fuzzy sets, we say that this H with respect to this Px also satisfies another property. So take an x dash and construct its fuzzified set a dash. What we want is that given this covering, look at this formula, it says that it can intersect some fuzzy sets in this collection Px, but intersect in the sense of the support of this a dash, h of x dash, it intersects at most two fuzzy sets, the supports of two fuzzy sets in the collection here. So essentially it says that given a covering, which is collection of fuzzy sets, and an x dash, the fuzzified version of x dash should at most intersect with two fuzzy sets from this covering, from this collection. That means the support of the fuzzified set should intersect at most support of two fuzzy sets in this collection. Let's look at an example. We have seen this as a collection of 5 fuzzy sets as just a fuzzy covering. We see clearly it's a Sub-Ruspini partition. That's where we have seen this collection of fuzzy sets. And we can come up with a fuzzification such that the fuzzified set intersects at most 2 from this collection. For instance, if we consider this as a x dash, then this is one fuzzification, which is also normal, which intersects at most 2 such fuzzy sets in this partition. It is not really very difficult. For instance, if you are given these AIs, which form a Sub-Ruspini partition, so now if you consider support of, we know that because these are normal also, we know that support of AK can only intersect support of AK plus 1 and AK minus 1. So now let's consider this to be nu k. Some set, or for the moment let's just take this to be AK, BK, because it's coming from K. So essentially for every one of them you are going to get this. All we need to do is find the length of this, let's call it LK. Now infimum over I is equal to 1 to n of Li's. If you consider these, n minus 1 perhaps, because you can go to that. If you take this as the corresponding L, then if you ensure that the fuzzifier does not fuzzify a given point to a fuzzy set whose support is bigger than this, then such a fuzzifier can be considered. So given the partition, based on the partition or the fuzzy covering Px, we could always come up with such fuzzifiers. Such fuzzifiers do exist. Now we are in a position to state the main result of this lecture, which deals with monotonicity of f star with respect to the alpha cut based ordering. So let's consider such a model of SBR where AIs form from the antecedents, they form PX and they form a Sub-Ruspini partition on X. Note that these are all coming from F star of X. That means each AI is normal, convex, continuous, and it's strictly monotone on either side of the kernel. The BIs are the consequence, they form PY. However, they form a Ruspini partition on Y. And once again, they actually come from F star of Y. That means on that domain, these are essentially normal, convex, continuous, and strictly monotone on either side of the kernel. And we have these consequence and antecedents, they are orderable and with respect to the alpha cut based ordering, and they actually form a strictly monotone rule base. Now let's start specifying what the other functions are: J, M, G, H, and G. We take G to be a T-norm and J is any fuzzy implication satisfying OP. M satisfies Mi, that means it is insistent on f of x. It satisfies MCP, that means it's with respect to Px, it is essentially insisting on being consistent, and it also has specificity with respect to the alpha cut ordering on f of x. Now, we pick a fuzzifier H such that it has those two properties that we saw before. That is, if given x dash is smaller than x double dash, we know that the corresponding fuzzified outputs A dash and A double dash, they are orderable accordingly with respect to the alpha cut based ordering. And also when we take P of x and any such fuzzified output A dash intersects at most two fuzzy sets from this collection. And for the defuzzifier G, we take the least of maxima. So essentially, if the output fuzzy set B dash is normal, that means if it has kernel, then it is the least of the kernel, the smallest, or the point at which the output B dash takes its first point of normality. Well, if you consider these as the operations and as the collection of fuzzy sets with these properties, then it can be shown the system function f star of f SBR, the model that we are considering, is in fact monotonic. Once again, we will keep the important parts on the screen so that AIs form a Sub-Ruspini partition on X, BIs actually form a Ruspini partition on X, G is a T-norm, J comes from fuzzy implication that satisfy OP, and M satisfies these three properties: insistent, consistent with respect to Px, and also specific on the overall space of fuzzy sets. And H is a fuzzifier which has those two properties, comes from the special class of fuzzifiers, and G is the least of maxima defuzzifier. Let's look at the proof of this. To begin with, let's assume that we have x dash coming from x, and now let's look at support of an AK as the interval xk minus 1, x as being contained in this, because remember we are considering a Sub-Ruspini partition. If xk minus 1 is the point of normality of ak minus 1, that is our usual notation convention. So that means support of AK will be contained in this, perhaps strictly contained in this should be said, so that they do not intersect. So clearly the supports do not intersect because you are looking at supports do intersect, but they will not overlap with the kernel. The closure will not intersect with the kernel of another fuzzy set. Well, so now given this x dash, we are going to apply h of x dash to obtain an a dash. Note that given this px, we know that a dash, the support of a dash, if it intersects with support of ak, then this implies that there are only two fellows, k is equal to sum m plus 1, n plus 1, Now, once again, we are given x dash element of x. Clearly, it has to fall in one of these intervals. So let's assume that x dash in fact falls in this interval xm plus 1. As in the case that we discussed when we discussed the proof of monotonicity of an FRI, let's assume that x dash belongs to xm plus 1. Now, the first step here, proof proceeds more or less along the lines of proving the monotonicity of an FRI, but of course there are few differences. In this case, we specifically consider Sub-Ruspini, because if you had Ruspini, then such a falsifier is not possible, because at the points of normality you cannot have a fuzzified output which only intersects two fuzzy sets in the partition Px. Hence we consider a Sub-Ruspini partition. Further, if we consider Ruspini partition and a singleton fuzzification, then more or less it essentially goes down to the case of discussing an FRI, either a CRI or BKS, depending on the J that we consider. Hence, just to ensure there is some amount of generality, we are discussing a situation, a context, a setting where we have a Sub-Ruspini partition on AIs and we are considering a different kind of fuzzifier. Of course, H can also be a singleton fuzzification, because then it will not intersect more than two fuzzy sets in this context, because the Px is formed in that way. It is a Sub-Ruspini partition and each of the fuzzy sets is normal, convex, continuous and strictly monotone on either side of the kernel. So the first step is to show the output B dash is essentially this. So we know that B dash of y is in fact G I is equal to 1 to n. Now G is T for us. J is an implication M of A dash comma AI comma Bi of y. Note that by an assumption on H, A dash intersects only two of them. Let's assume, since x dash comes from xm plus 1, it is clear then A dash, when we fuzzify it, when this x dash is fuzzified to A dash, it is going to intersect only the fuzzy sets am plus 1. Now, that means support of A dash, intersection, support of A k, when k is not equal to m plus 1, this is in fact equal to 5. Which means this implies m of A dash ak for k not equal to m plus 1, this is equal to 0, because we have taken an m which is insistent on f of x. That means unless the supports intersect, the matching values are going to be 0. So in essence, what we have now is this B dash of y reduces to only considering T of J of m A dash am comma Bm of y and J of m A dash am plus 1 comma Bm plus 1 of y. Once again, this is the similarity value. Let's write it as Sm, and this similarity value, let's write it as Sm plus 1. So what we are left with is T of J of Sm comma Bi of y comma J of Sm plus 1 comma Bm plus 1 of y. So this is what we have here in terms of J, which is an implication written in terms of the arrow. Now, the next step is to find the kernel. So does this B dash have a kernel? Is this B dash normal? Once again, let's work this out. We show that kernel of B dash is in fact, there exists some values am, bm, am plus 1, bm plus 1. That this happens. This is what we need to show. Note that as in the case that we have seen, we have A's which do not form a Ruspini partition. Just for illustration purposes, let's take triangular fuzzy sets. We know that Bm and Bm plus 1, they come from Py, which does form a Ruspini partition on Y over Y. So if we take Sm, let's take this to be Sm, and let's take this to be Sm plus 1. We see that once again we can work out the number. What we want is the kernel of B dash. Now this is clearly set of all y, element of y, such that B dash of y is equal to 1. Once again, T is a T norm, that means both of these should be equal to 1. Is nothing but set of all y such that Sm implies Bm of y is equal to 1, and the other one, intersection y such that Sm plus 1 implies Bm plus 1 of y is equal to 1. We know that implication J that we are considering is an OP implication. That means this is set of all y such that Bm of y is greater than or equal to Sm, intersection set of all y such that Bm plus 1 of y is greater than or equal to Sm plus 1. So essentially what we are looking at is Bm, the alpha cut at Sm, intersection the alpha cut at Bm plus 1 value Sm plus 1. Once again, let us color this. So if this is Sm plus 1, then we are looking at this as the alpha cut, and this is plus 1 the alpha. So clearly, as in the previous case, we take this to be Am, this to be Bm, and this to be Am plus 1, and this to be Bm plus 1. So clearly, because of continuity of Bi's, we know that if it is continuous, strictly monotone, it is onto there on the domain, which means for every value of Sm plus 1, there will exist some value on y, which we are calling it as Am Bm, and Am plus 1 Bm plus 1, such that these happen. So this is essentially Am comma Bm, intersection Am plus 1 comma Bm plus 1. Note that just to be more specific, Bm of Am is equal to Sm, is also equal to Bm of Bm, and Bm plus 1 of Am plus 1 is actually Sm plus 1, which is also equal to Bm plus 1, Bm plus 1. So we have obtained what we wanted to get. The kernel of B is in fact intersection of these two. Of course, we need to show that this kernel is in fact non-empty. That means there is some intersection available. That's the third step. Let's show that kernel of B dash is in fact Am plus 1 comma Bm. Now firstly, notice one thing, that we are talking about Am and Bm being acted upon by Bm, and Am plus 1 and Bm plus 1 being acted upon by Bm plus 1. That means all of these Am, Bm, Am plus 1 and Bm plus 1, they actually belong in Xm plus 1. So this much is clear. Ym plus 1, because we are looking at fuzzy sets on Y. Now so that means it is clear that Am is smaller than Bm and Am plus 1 is smaller than Bm plus 1. if we can show that am plus 1 is smaller than bm, then clearly, because these are intervals, we are looking at convex fuzzy sets. So that's why every alpha cut is an interval on R, because that's what we are considering as the domain. X is a subset of R. So it is clear, all we need to show is that am plus 1 is less than bm. Then clearly, the kernel of b dash will be this. On the contrary, let us assume that am plus 1 is in fact greater than bm. Now this implies, if you apply on this domain ym plus 1, we know that bm plus 1 attains its normality at only ym plus 1. So that means bm is strictly monotone and increasing over this interval, over its support. And since we have these falling in this interval, if we take bm plus 1 of am plus 1, this is greater than bm plus 1 of bm. Note that bm plus 1, am plus 1 is in fact sm plus 1 is greater than. Now we know that on the output space y, bi is indeed form a Ruspini partition, which means bm plus 1 can also be written as 1 minus bm of bm, because it is bm plus 1 that will be intersecting over this interval ym plus 1. But what is bm of bm? It is in fact sm. So that means this implies sm plus 1 is greater than 1 minus sm, or that sm plus 1 plus sm is greater than 1. But note that this is a contradiction. Why is it a contradiction? Because we know that AIs are Sub-Ruspini. So that means the matching values, when we give these this corresponding similarity values, can at most be 1. We know this because it's Sub-Ruspini. When we give this, it cannot be greater than 1. So which means am plus 1 bm is in fact not true. This implies am plus 1 is less than bm, and from there we get the kernel of b dash, which was am bm intersection am plus 1 bm is in fact am plus 1 comma bm. So we have successfully shown that kernel of b dash is non-empty, and it is in fact given as am plus 1 comma bm. When you apply g on b dash, it is least of maxima on b dash, which is essentially am plus 1. So finally, we need to show that when you are given two inputs x dash and x double dash, if they are ordered monotonic, x dash is smaller than x double dash, we need to show g of x dash is in fact smaller than or equal to g of x double dash. So let's show this. Note that x dash is given to be less than x double dash. We know that from the above, g of x dash will be some m plus 1 dash, and g of x double dash will be some am plus 1 double dash. All we need to show is that this is in fact smaller. This is what we need to show. Let's see how to show this. We know that x dash is less than x double dash. Let's keep it to be strict less than. Now, if you consider h of x dash, then we know that by the kind of fuzzy that we are considering, the corresponding outputs A dash, A double dash, they are in fact orderable with respect to the alpha cut based ordering. So that means we have A dash is orderable with respect to this. Now this means M of A dash, any A in particular AM is greater than M of A double dash AM. But M of A dash AM is nothing but SM dash is greater than SM double dash. Once you have SM dash is greater than SM double dash, note that on the BIs we do have, these are similarity values, we do have Ruspini partition, which means this is essentially, take it as 1 dash, which is SM plus 1 double dash, dash is less than SM plus 1 double dash. Because of Ruspini partition, we have this 1 minus this. Now this implies, now once again these are similarity values. SM plus 1 dash is essentially, we go back here and see, SM plus 1 dash is BM plus 1 of AM plus 1 dash. This is less than BM plus 1 dash AM. BM plus 1, BM plus 1, AM plus 1 dash. Now remember, BM plus 1 on this interval is strictly increasing, which means the corresponding A dash M plus 1 is less than A double dash M plus 1. But this is essentially G of X dash. This is G of X double dash, which means this is smaller than this. So all we have made use of are the properties of H, M, and the fact that J has OP, and on the antecedent side we have a Sub-Ruspini partition, and M is in some sense compatible, consistent with respect to Px, and also the fact that on the consequence Bi we actually have a Ruspini partition. So this shows that whenever X dash is less than or equal to X double dash, we also have G of X dash is less than or equal to G of X double dash. So this completes the proof, and what we have shown now is, with respect to the alpha cut based ordering, we in fact do have monotonicity of an SBR under the conditions that we have seen. When you choose the different components in the SBR model properly, appropriately, we can ensure monotonicity of the corresponding system function as a function from X to Y. With this, we will wind up with the discussion on monotonicity of FIS. A few reference works should be highlighted. There is quite a bit of literature discussing monotonicity of similarity based reasoning schemes, especially the TSK fuzzy systems. So this is one of the works that you can look into. The works are also quite distinct in their approaches. The one that we have taken now in this lecture is to look at it in generality and fix the conditions on the components of the SBR model which will ensure monotonicity. However, the works do differ. For instance, here like the conditions on the parameters are specified here in this work, similar to ours. Here they have assumed smooth fuzzy systems and then they are discussing monotonicity of those. It's quite a recent paper, and so you know it is clear that the interest in monotonicity of fuzzy systems is still quite hot and alive. In this paper, quite interestingly, they discuss multi-input fuzzy rule based models, whereas in the lectures we have only considered single input, single output rule basis. And this is yet another paper which discusses monotonicity of fuzzy inference method, especially the TS inference method. As was mentioned, these are only some sample works. There exist many more works This is only highlighted for the different approaches that they have taken. For instance, the paper by Tay and Lim, they actually are looking at rule interpolation techniques to make sure that the multi-input system that they get is in fact monotonic. Well, with this we come to the end of discussing monotonicity of a fuzzy inference system. What lies ahead? In the next week, week 12, which also will happen to be the last of the week for the lecture series that we are going through on this course titled Approximate Reasoning Using Fuzzy Set Theory, we will look at the computational aspects of fuzzy inference system. So far, in the last few weeks, we have discussed some desirable properties of a fuzzy inference system, that of interpolativity, continuity, robustness, and monotonicity. But in some sense, all of them deal with what could perhaps be categorized as the correctness of a fuzzy inference system. We haven't seen the computational aspects of it. We have seen that a lot of the properties, thankfully coming from residuated lattices, they helped us in discussing and proving many results. However, if you recall, these are in the form of either equations or inequalities. These equations and inequalities involving either the minimum, the meet or the join operation of the lattice and the t-norm or the implication coming from it, they are also available for other classes of fuzzy implications. In the last few weeks, we have looked at using these properties towards justifying the correctness of the inference system that we are considering. But in the next week of lectures, we will look at these functional equations and functional inequalities, for which classes they are available outside of this class of R implications. Some of them we will discuss, and also their impact on the computational aspects of fuzzy inference systems. So this is what we will take up in the set of lectures in the next week, the last week of this lecture series. We will discuss the computational aspects of fuzzy inference systems. Glad you could join us today for this lecture. Hope to see you soon in the next lecture. Thank you all.